Okay, welcome everyone to the 141st meeting of new directions in group theory and triangular categories. Our speaker today is Jan Stovicek from Charles University Prague, and he'll be talking to us about torsion and complete dualizable objects in TT categories with a Noetherian ring action.
Okay, thank you very much, and my apologies for the very long title. So this is a talk on a preprint with Jun Maillard, who is actually, I think, in the audience. Let us start. So I'll first try to motivate what we did by some maybe more classical example. So let's look at this problem or this setup. So let us take a commutative Noetherian ring, right, and some ideal, any ideal we want. And then we can try to look at modules supported only at VA, right, at the corresponding Zariski closed subset. So in practice, right, every module has a unique largest submodule which is supported, where we take all elements annihilated by some power of this ideal A, right? So these torsion modules or modules supported in VA form a hereditary torsion class, and we have the torsion radical, which could be expressed as some direct limit of Hom groups, right? Because of course these Hom groups from R over AN just picks elements annihilated by A to the power of N. And I mean, if we derive this torsion radical, we actually get a recall more. This is something maybe these days already classical. So we have, what do we have, right? So we have the derived category of the ring, and we have the derived category, the full subcategory of the derived category, uh, formed by complexes whose cohomology is supported only in VA, right? And then we have the inclusion. So this is this upper left arrow, and then we can take the Verdier quotient. It seems that I have here some subscript which shouldn't be there. So this should be just the derived category of quasi-coherent sheaves of the open subscheme. So this Zetor is superfluous here. It shouldn't be there, right? And so this is the Verdier quotient, and then we have two adjoints on both sides. So we have the direct image, and then we have one more, and by some abstract nonsense, I mean, so the inclusion was fully faithful, the middle functor on the right is fully faithful, and also the lower functor is fully faithful. Okay, so far so good, and but then there is more, right? So we can look at some compositions. So we can look at the composition of the functors, some endofunctors of the R, right? So we can first take the middle functor on the left, and then compose it maybe with the upper left fully faithful functor, and then what we get is just the right derived functor of the torsion radical, essentially, if we compose those two. And okay, it's not completely obvious, but it's relatively well known, and I will take it as a fact here, and it's a version of what is usually called local cohomology, right? And this is very classical. But then we have something which is more recent, but still relatively old, studied by several people. And because we can take also this I upper star and then compose with I lower star, which is also a fully faithful functor. So we get another functor of the R, which is actually right adjoint to this gamma A. And the funny thing is that what it does, it's really closely related to the completion, right? So I mean, we can take the a-adic completion functor. So this is what is written down there, and we can this time take the total left derived functor. So the a-adic completion somehow looks formally dual to this torsion radical, right? So here we take tensor with the factors, and then we take inverse limit. And I mean, it looks a little bit strange. So there's the right adjoint to the right derived functor of the torsion radical is the left derived functor of the adic completion. So this is again, there is some theory behind that, and it's actually not obvious even for commutative Noetherian rings, and but it works more generally. This was studied by Greenless and May in 1990s with some motivation from from the homotopy theory, and then by many other people maybe interested more in the algebraic aspects. And somehow the point is that, I mean, this is always a mixture of left and right exact functors. I mean, both the torsion radical and the completion. And the completion is not such a nice functor. It's okay, it's a well-known consequence of the Artin-Ries lemma that it's exact on finitely generated modules, but on big modules it's neither left nor right exact. But in the process of deriving it, the problems kind of miraculously disappear. So, okay, we have this, and this is some standard picture. Okay, so because I was copy pasting something in my presentation, so my apology for that, but this ZTOR subscript should be ignored everywhere from now on, I'm afraid. And but okay, so now we have this notation, and just maybe a few other features of this picture which I want to point up is that okay, we have some other functors in the recall mode which are standard, so this should be somehow mirror images or upside down of this gamma and lambda, so I call them LA and VA, right? And so these are some compositions of the right of the functors in the right half of the recall mode. And the thing is, I mean, first there is some piece of abstract nonsense. This happens for every recall mode. So every recall mode gives rise to three subcategories of the R. There are three fully faithful functors, and it gives rise to something which I would call a torsion free triple, right? So I'm convinced that most of you know that these could be viewed as two semi-orthogonal decompositions of the A adjacent to each other. The two classes on the left and the two classes on the right form semi-orthogonal decompositions. So there are some functorial triangles, and or sometimes people call these pairs Bose-Field localizations. So this is essentially the same concept, right? So basically, what we can say that every object in the R admits a unique triangle and even functorial, which has the left-hand side part in gamma A and the right-hand side part in LAT, or there is a similar triangle unique for every object, just where the objects are from the right two classes, and so on. So I hope you can ask, of course, please stop me if there is anything which is not clear. But maybe there is one more part which will be interesting because the ring is commutative, so we have the tensor product, we have the derived tensor product, and this is something which I want to heavily rely on here. So the category dr is tensor triangulated, so it's monoidal, even close monoidal, right? We can take the derived tensor product over R, and then the if we tensor two complexes and totalize, then the result is again a complex, and we can derive that, left derive that, and we have R-hom, which is the right derived functor, right, and so on. And this actually, so what I will be really interested in would be in this category of objects supported in VA. And this is actually itself a closed monoidal subcategory. This is something interesting. So in the first place, what is known again from some theory, for example, from Neeman's classification of localizing subcategories and the theory around that, which is connected to it, is that this dVAR, which is equivalent to the essential image of I-Laverschrieg, which is the same as the essential image of this derived torsion functor gamma. So this is a tensor ideal. So if you tensor a complex with torsion cohomologies with anything else, you got a complex with torsion cohomologies. So in particular, I mean, the tensor product, the derived tensor product restricts to that subcategory. It actually becomes monoidal, but now the tensor unit is different. The tensor unit is not the ring itself because it's not in the subcategory, but you can take the derived torsion part, and this will become the tensor unit. So this is actually monoidal, symmetric monoidal category, and it's closed. But again, if you take a derived Hom of two complexes with torsion cohomology, the resulting complex need not have torsion cohomology, but you can again take the torsion part, you can take the torsion coreflection, and this will become a completely valid R-Hom, right? And you can do something similar with the essential image of I lover star, which is the same as the essential image of this lambda, which is the derived completion functor, right? And this time R-Hom actually is just inherited from the R, but the tensor product needs to be completed. But it's still closed symmetric monoidal. And the tensor unit has to be completed this time. For example, if you start with an a-adically complete ring, then you don't have to complete it anymore, right? But but now there is much more symmetry in the picture than in the underived sense, because in the underived sense, of course, torsion and completion is something which is quite different. But once you derive the picture, then these two categories will get identified. There is a canonical equivalence between them. So let's look at that. So I'll just keep the recall more with the same typo, which will be everywhere through the presentation. And okay, so there are two facts about that, two maybe interesting facts. So then also the essential image of this lambda A of the derived completion is given cohomologically. This is something which is not obvious at all. So an object is in the essential image of the derived completion if and only if each cohomology is such. So each cohomology is derived complete module, which means that it's that M is okay. M is derived complete. So okay, I told that the completion is neither left nor right exact. So just by brute force, we can amend that, and we can take the zero derived functor of the completion, and we can call a module derived complete if it's in the essential image of that. So equivalently, you can say that, I mean, that it has a presentation of this form, where this is I-adic completions of free modules. So of course, that's has something to do with we take the left derived functor, right? It's more or less the thing. And so what is this I-adic completion, right? It's a bigger than the usual direct sum. It contains all sequences of elements which converge to zero. So they may be it's something between the sum and the product, and it should be some kind of decaying sequences, right? And then we have also something which I call the Matlist-Greenlist-May equivalence, or it's a part of what people usually use under this term or refer to under this term, or sometimes people say duality also, but strictly speaking, in the form in which I want to use it, it's an equivalence, right? So if T is dr, so then for formal reasons, if we have any recall more, so the essential image of I lover shriek and I lover star are equivalent. This is again some formal nonsense, which you can see, for example, if you know about semi-orthogonal decompositions. But the interesting part, and I don't know who noticed that, it's nothing too deep, but I saw it explicitly in work of Benson, Iyengar, Krause, and Pevtsova, quite recent. To spell that out, I mean, this is even a strong monoidal equivalence. So it preserves all the structure, including the strong monoidal structure, right? So the funny thing is that in the derived sense, there is actually a little difference between taking derived torsion and derived completion, at least if we have a commutative Noetherian ring. Okay, and but then okay, so I want to look at not at all objects of the derived category, but then there are some interesting objects which are small, and this will be actually the point of the talk. I want to look at compact objects and dualizable objects and some interaction between them. So just to recall the definitions very quickly. So okay, if we have a closed monoidal category, then we have internal Homs, and with such an adjunction, so for example, we can have the derived tensor product and R-Hom, right? And an object is compact, so this is quite standard definition and frequently used, right? That it preserves coproducts or sends coproducts in T to coproducts of abelian groups. Maybe something more special, but I think still quite well known, is dualizable objects. So we basically say that an object is dualizable if the internal it's some kind of enriched version of compactness, kind of. It looks a bit different, but if you look at the definition, so for example, if an object is dualizable, then the internal home preserves coproduct, because the internal home is essentially tensoring by the dual of D, right? But it's more than that. And in our example, or in the example of basically the derived category of any commutative ring, so the compacts and the dualizables actually coincide, and these are perfect complexes. Right? So this is something which is also quite standard. And in that case, people, or at least some group of people, call such categories compactly rigidly generated tensor triangulated. So a triangulated category which is with a compatible closed symmetric monoidal structure, which is compactly generated, and compacts are the same as dualizables, or in some other terminology they are called rigid. So this is why the terminology. So we have such categories. Okay, but now let's look at the recall more again, and let's look at this category gamma A, because now if we have this recall more, right? So maybe T is very nice and it's compactly rigidly generated and Z triangulated, but what can we say about gamma, right? It has again some closed monoidal structure. So for LAT, for the localization, it's known it has essentially the same properties, but for gamma, it becomes a little bit tricky for the derived torsion or derived complete complexes, right? So what happens here is that this category is again compactly generated. So far so good. So it's triangulated with a compatible tensor structure, and it's compactly generated. And if you want a specific compact generator, so then you can take any sequence of generators, and you can take the Koszul complex, so some very standard object. And the category is compactly generated. Okay, and as I told, it's by Brown representability. You have internal homes, or we can even write down a formula specifically, and that's all. But the problem is, sorry, another typo. Here I meant really the tensor unit, right? So R is missing here. So the tensor unit of gamma AT is typically not compact. So let's illustrate it on a simple example, right? So why not? We can take the ring of the integers, and we can take any prime we like, right? But what is then the right-derived torsion? So what you should actually do, if you compute that, you can take the injective resolution of the ring of integers over itself, which means you embed it into the rationals. Then you take the direct sum of all prefer modules, and then apply the torsion radical, which picks just one of the prefer modules, which will live in degree 1. So it's shifted. So the tensor unit here is the prefer module shifted in degree 1, and this is certainly not a perfect complex. Okay. So it's not compact. So this is and this is quite typical. I mean, it's very often not compact. So this is what you can roughly expect. And so what happens here is still that the dual that in this tensor triangulated category gamma AT, there are in this situation always more dualizable objects than compact objects. The tensor unit is always dualizable, but it need not be compact. So we lose the equality, we get just an inclusion. And what I want to tell you, I mean, what is the story about, is that the dualizable objects is sometimes better behaved than the compact objects in this sense. So maybe this is the category which we want to look at closer. What happened here? Yeah, there is some problem with spacing, obviously. Um, yeah. Okay. I mean, maybe we can ignore the part which is not on the screen. Sorry for that. What we have anyway is that the torsion dualizables and complete dualizables are the same, because we have an equivalence respecting all the structure. And so if you look at dualizable objects, then we again get the same. And so why I'm mentioning that is that the complete dualizables somehow are better behaved in this particular example, but they are completely equivalent to torsion dualizables, and torsion dualizables are sometimes more pleasant to work with in the abstract setting, right? Okay, but the interesting thing is that it's a very natural object, but I don't know, it's not, it seems it's studied more in depth or computed in examples only very recently, like units of years, 2024, 2025, or maybe 2022 or something like that, right? So let's look at this particular example. So if we have a commutative Noetherian ring, and if we have an ideal, so what are the torsion dualizables, right? So if I say this is interesting, maybe it would be better to say what they are, right? And what they are is actually, the funny thing is that they actually identify with perfect complexes over the completed ring, naturally. There is a natural identification like that. So in a special case, when the ring was local and it was a maximal ideal, this was proved some time ago by Benson, Iyengar, Krause, and Pevtsova, and in quite in even a greater generality than I stated here, even in under much weaker condition than commutative than Noetherian. For many more commutative rings, it was recently proved by Malber and Sanders, right? So if we want to look at this conceptually, so first of all, the tensor unit is not compact, but it's dualizable. So if we want some small tensor triangulated category attached to the completion, it should be this one, not the compacts. And second, in the classical situation, this abstract completion really gives what we would expect from the ordinary completion, right? So this is quite interesting, and this is, I think, why people looked at that, or some people looked at that recently. And just to the context, right? So why we can hope, we can dream a bit, right? So from the abstract point of view, Paul Balmer suggested try to view small tensor triangulated categories as some kind of ring-like object when the direct sum is like something like the addition, and the tensor product is something like the multiplication, and he built quite some theory about that, right? And he defined the spectrum, and he defined some other concepts. And so this was like what is now called tensor triangle geometry, right? And okay, of course, one can define various things, but this was a really interesting and useful point of view, because this really allowed to transfer some ideas from algebraic geometry to other settings, like representation theory of finite groups, or spectra in the sense of topology, so some homotopy theory, and there are many more examples of that kind. And this above theorem, and also some work of Naumann, Paul, and Ramsey, and some other authors, I guess, by now, because it's quite active field. It suggests that, okay, so what do we have, right? If we start with a rigidly compactly generated tensor triangulated category like the R, so where we assume that compacts and dualizables are the same, then this torsion, derived torsion radical gives us a functor, right, from TC, and this gamma is actually compatible with the tensor product. So it gives a strong monoidal functor, and every strong monoidal functor preserves dualizables. So we have something like a completion functor from the original compacts, so something like the perfect complexes over R, to the dualizables, torsion or complete dualizables as we wish. And if you look what this equivalence is, then you actually can identify this with the completion functor, right? If you want, if it's on perfects like complex bounded complexes of finitely generated projectives, you don't even need to derive it. It's really the completion functor, right? So we may hope for, if we dream a bit, that this would be a good model for the a-adic completion in this TT geometry, right? And now let's look at, let's bring some other evidence that this actually might work, right? So I'll try to now fix the abstract setup, just to explain you in what way in which direction we generalized some of these results, and then let's look at what really can be proved about that, right? So from now on, T will not be just the R, but it will be a compactly generated triangulated category. Then again, I want it to be a tensor triangulated, so with a compatible monoidal structure. So I mean, there are some precise axioms, for example, in a memoir by Hovey, Palmieri, Strickland, even though they use quite different terminology, because they view every such category as an abstract homotopy theory. Okay, so if we have compactly generated triangulated category, we automatically get internal Homs because we have Brown representability, which allows us to represent functors, and if we represent this functor, we just get internal Homs. Okay, I will assume that compacts and dualizables are the same. This is an assumption which works for many examples like derived categories of commutative rings, or I will show some more examples in a minute. And so I will call this, as I already mentioned, rigidly compactly generated and the triangulated categories. Okay, so far so good, but then I will add some more restrictive assumption, which is still satisfied in interesting classes of examples. I will assume that there is an R-linear action over a graded commutative Noetherian ring, right? So of course dr itself, for if R is a commutative ring, then its derived category is enriched over itself. So it's, no, sorry, what I wanted to say that the Homs, the usual Homs are linear, are modules again, right? The usual Homs between complexes are R modules. But here I will want some graded action, so I will view the triangulated category as a graded category. So from now on, whenever I say Hom txy, then I will mean the graded abelian group, where in degree n, this will be the group of morphisms from x to y shifted by n, right? And this makes sense, and so we can view T as a category not only additive but enriched over graded groups. But I want that these are just not graded groups, but they are graded R modules. So there is some R linear action, right? So you can really view it as a generalization of R linear categories in the usual sense over commutative rings, but now everything is graded because triangulated categories have the shift functor, and so they are naturally graded up to fixing it technically a little bit, right? And but I want to use Noetherian condition, right? So I want that actually the action is not so bad, in the sense that the Hom R modules are Noetherian or equivalently finitely generated, whenever this makes sense. And this makes sense at least for the compacts, right? So I want that the Homs between compacts are small. They are finitely generated over the base ring. And so this is the basic setup, right? So I mean, on one hand, it's restrictive, but on the other hand, there are many interesting examples. So one of them is what I showed before, right? So it's kind of trivial, but I mean, what we can do, right? At least we can consider some DG algebras or infinite ring spectra whose cohomology ring is graded commutative Noetherian, right? And then we have some examples maybe from derived algebraic geometry or derived commutative algebra or whatever we want to call it, right? And then of course we have the structured object, the DG algebra, but then we have the cohomology, and this if the cohomology ring is commutative, is Noetherian, then we're fine. Okay, but then we have a different type of example, which is of course studied before, but I mean quite intensely studied in the last decade or more by Benson, Iyengar, Krause, and Pevtsova. So you can look at the homotopic. You can take a field, a finite group, and you can look at the homotopic category of injectives, which is the same as projective modules over that, right? And this is a compactly generated triangulated category. And then you use the tensor product over the base field using the Hopf algebra structure, so the usual tensor product of representations of groups. And this, in this case, I mean, the acting ring is the group cohomology, which is the graded endomorphism ring of the tensor unit, or the Yoneda algebra of the trivial representation. So in fact, I define this ring as an extra datum, more or less inspired by BIKP papers. But in fact, when I assume that the endomorphism ring of the tensor unit is finitely generated over the base ring, right? Then for most practical purposes, I can really assume that R is the endomorphism ring of the unit because it's just a finite extension, module finite extension of the ring I might have started with. So typically it's no harm to replace R by this one. So, and we can combine the above. So there is some recent work by the BIKP group together with Toby Bartle, and so we can take a commutative Noetherian ring and either a finite group or even finite flat group scheme over that, and then we can take some triangulated category attached to that, such that compact objects would be G lattices, so some representations which are, I think, finitely generated, which are perfect complexes over S, I think. Oh, so no, I think there is an, how is it? There is an exact category of lattices, which are representations which are finitely generated projective over S, and then we take the derived category of those. I think this is the correct setup, and then they have to incomplete it using some, let's say, theory of infinity categories or stable infinity categories. So starting from TC with some enhancement, they produce all of T. Sometimes under some more restrictive assumptions, there is a more concrete description of that, right? So these are some kind of stacks. And then again, we have a group, we have the cohomology ring, which is finitely generated, and there are some relatively complicated results, long papers about that by Lau and van der Kallen, quite recent. So I just trust them here. Okay, so we have some examples of this kind. And the ring action is more tricky, right? Because the acting ring is just the cohomology ring. And what we try to do from the conceptual point of view is follow the BIKP style of work and try to prove as much as we can without using any enhancements. That means what we can do is that in such setup is to just look at the action of the cohomology ring on the triangulated category in question, right? So this has, of course, some limitations, and the pros of this approach is that it's more elementary than working maybe with some infinity category theory. But here it seemed to work to quite some satisfaction of our, at least. Okay, and so okay, we get basically the same picture as before as for rings. So if we take a triangulated category of this type with a nice enough action of a graded commutative Noetherian ring, and if we take any homogeneous ideal, so this time we are in the graded setting, so we look at ideals generated by homogeneous elements. So we can look at the class of power torsion elements, right? And so if you look at the definition and compare it with the previous definition over a ring, so you see that it's defined again more or less in the same way, cohomologically, right? If you imagine for T the derived category of an ordinary commutative Noetherian ring, and you take for C the ring itself, which is a compact generator, so this definition would tell you that you're looking at complexes with torsion cohomology, right? So in that sense, if we want to somehow model cohomologies, so then we should look at Hom groups from the compacts, right? So we again give a definition which say that torsion objects are cohomologically torsion on Homs from the compacts. So this is in this sense a natural generalization, and then there are some standard results studied by all the authors mentioned before, or many of them. So I mean, we get again a recolmo of roughly the same type, right? So we have the same kind of functors coming from the recolmo, which are now just more abstract, right? And this gamma is some kind of derived torsion radical, so it is a correflection with respect to this, or correflector with respect to this gamma AT, right? And we again can view the recall more as a recall more as some kind of TTF triple, so as a pair of two adjacent semi-orthogonal decompositions, and this is all quite abstract. And we again have this sort of abstract form of the Matrix-Greenlist-May equivalence, right? So we can derive, so torsion and complete modules are the same. But maybe the first interesting part is that before even the derived complete modules were given cohomologically, and we have the same here, right? We have so we can also look at derive a complete R modulus over a graded ring. The theory is completely analogous. And it again turns out that the essential image of the completion functor, which is this last class here, which is the same as the essential image of this, is given cohomologically. So we can test it on Homs from compacts, and the result should be a derived a complete module. Okay. So this is good because this is promising because this allows us to translate problems about derived completion again to some problems about modules or about Hom modules, right? Hom R modules. Okay, so far so good. So but now what survives in the abstract setting from the category of rings? There were some more properties, and it seems that again many crucial features survive. So again, this gamma AT, again, if I go a little bit back, this is a tensor ideal. Gamma AT as a class is a tensor ideal in T. So we have again a symmetric monoidal structure, when again the tensor unit is the only thing which has to be kind of forced into the class. We need to take the correflection, and then again this gamma AT is compactly generated. Now it's generated by some Kosul object. So we do basically the same story, the same thing. It's roughly the same story. We take our ideal A, we take a sequence of generators, and then we take some Kosul object, and I mean there is some formal way to describe that. So what we take, we basically again take one by one. We take the multiplication of the action of A1 on C. We take the cone of that. Then we take the cone of the action of A2 on the cone, and so on and so on, or we can write it in this way. The only thing is that our elements are A now have a degree different than 1, so we have some suspensions, but it's very similar. Right, and now again the compacts of compact torsion objects, compacts in the category of torsion objects is actually the same as the compacts in the bigger category T, which are torsion, and they are included in the dualizable torsion objects. So that means in the dualizable objects in the tensor triangulated category of torsion objects. And we, of course, cannot expect this to be an equality because this was not the case for even for the simplest, one of the simplest examples we could take, right? And now the thing is that we can express this tensor unit as a homotopy colimit, as a sequential countable homotopy colimit in this triangulated category of some Kosul objects, right? So we can again approach it from the compacts, but the sequential homotopy colimit is not compact, right? Or it's definitely need not be compact, right? And now, even abstractly, we can look at the dualizable objects. So then, this is a small tensor triangulated category, and then we have again something like the torsion functor. Or you can, of course, because of this MGM-like equivalence, we could do the same for complete objects. So I will view this as some kind of completion functor, because I mean I could try everything with lambdas. Okay, very well, and then we can inspect to what extent this actually deserves the name completion. It actually seems that it does to quite some extent. So let's look at how this completion interacts with the action of the original ring, right? So okay. the naive thing to do, what we of course can do, if we take a say graded but still commutative Noetherian ring and some homogeneous ideal, so then we can take the completed graded ring, so the direct limit that you would expect just in the category of z-graded rings, so we can complete it. And then what we know, right, is the following. So we know that the endomorphism ring of the derived, of the torsion tensor unit is by the MGM the same as the equivalence of the complete tensor unit. It would be just better to have the a above, to have superscript here. But now, okay, this the complete side has the advantage that the completion functor is a reflection, not a correflection. So we can also rewrite it like that, right? So this is just by some universal property of the completion. And the tensor unit in the category T was compact, right? So and I told you that Homs from compacts to complete objects are actually derived complete R modules. So this is a derived complete R module, right? So this endomorphism ring is a derived complete R module. And now, okay, we have the completion, but this is actually not only completion, but it's a derived completion because this is the derived completion. This is the, okay, our completion at the module level is the completion, is the zeroth derived functor of the completion, but on projectives it works as an ordinary completion, right? And then we have this other functor, gamma, which takes this and completes it to that, and this is also derived complete, and just by, so now we have some square of graded modules, right? And just from the fact that this is derived completion and this is derived complete, there is some morphism, actually unique morphism of modules. But now if we play with it a little bit, we actually have a diagram of rings there, right? And as I told you that this could be safely, or if we want, and to replace R by this could be actually even an isomorphism. Here it's not so clear, but at least what we know that actually this gamma AT admits a canonical action of the completed ring. Why so? Because we have some kind of canonical morphism for R completed to the endomorphism ring of the tensor unit. And so if we want to act on any other torsion object, so we can, and we take an element of a ring, so we can move it here by this morphism, send it here by this morphism, and tensor it. So having such a morphism is another way to express that we have an action. Uh, so, so actually, by some formal, well, it's not completely formal. Actually, we need already to know something about the interaction of the action with the triangulated completion. But the upshot is that we get an R hat action on this category, right? But so this category gamma it is compactly generated. It has an action of the completed ring. Okay, there is something which this category behaves a little bit worse in the sense that compacts are not the same as dualizables, but maybe this is not actually an error. Maybe this should be more viewed as a feature. But if we want to do anything useful, what is missing at least is some finiteness condition, right? Because before in T, if we take the homomorphism group between finite objects, we assumed it to be finitely generated. And this is something which we do not know here yet, but I want to just show it on the next slide. So this is so if we so in this case actually the correct smallness concept is the dualizability, and so if we take two dualizable objects, two torsion dualizable objects, it turns out that that this is again a Noetherian or equivalently finitely generated R hat module. Okay, so we actually do get finiteness. And the proof is inspired by some arguments, more special arguments by Benson, Iyengar, Krause, Pevtsova. And they proved it for local rings and the maximal ideal, but we can prove it more general using some Nakayama lemma. So if the thing is that, I mean, if we have a derived a-complete graded R module, so something which is its own derived completion, and so then A is good enough. If M over AM is 0, and so A is the ideal with respect to which we complete, right? This is important. We cannot take just any ideal. And so if the factor over AM is 0, then M is 0. So this looks like Nakayama, and this cannot work at all for all modules, but this works for derived complete modules. Okay, so for complete, honestly complete R modules, adically complete modules, this is an older result, but it also works for derived completion. And and what we can do, I mean, it's not difficult to prove from that. If M over AM is an Noetherian R module, then M is actually an Noetherian R hat module. We do some standard tricks with Nakayama lemma, right? So the kind of A top detects finite generatedness. Right. So and this is how one can get this result, because I mean if we want to get this a top, so it's not exactly so we can compare it by Homs from a Kosul object here and play some relatively easy game which was described already by the BIKP group. Okay, so actually, if I want to summarize it, it's very nice, right? It's very nice in this setting that gamma it is compactly generated tensor triangulated, has in any reasonable sense an Noetherian R-head action, right? So of course the difference is this, that compacts are dualizables do not coincide, but the finiteness of Homs on the other hand works for the bigger triangulated category, and so in some sense we are almost in the same setting. There are some differences, but actually we can do even more. This was quite surprising to me, but basically using some arguments like the Artin-Ries lemma or something which seems to be quite related to that, we can actually prove that this abstract completion functor, like in the torsion incarnation, gives, if you start with two compact objects, and so actually between compact objects completion is really completion. Uh, which really has to do with the fact, at least conceptually, that completion, a-adic completion is an exact functor on finitely generated objects. So it's not, as far as I know, enough for the proof, but it's closely related, because if I want some sketch, so the thing is that, I mean, we want to look at the a-adic completion of the Hom group, right? So the a-adic completion of the Hom group is this, by the definition. It's some inverse limit. And we first need to move this tensoring inside, but we cannot move it inside literally. It doesn't make sense to tensor an object of T, but it makes sense to take the Kosul object, right? So we somehow compare this and that. And then the second thing which we need to compare, we need to move this inverse limit to some direct limit inside, and this is the best which we can get is a homotopy limit. And all of these concepts have to do with some inverse systems, and basically we need to get some control on the inverse systems, and there similar concepts appear as in the proof of the classical story with torsion and completion. There are some Mittag-Leffler inverse systems and some pro-zero inverse systems, and if you play a little bit on with them, you can get such things. Or some, this is related to the first derived functor of the inverse limit, because of course inverse limit is not exact, but in limit the things which actually make it more difficult vanish. That's roughly the message. And if we get from here to there, then it's actually already an easy game, because I showed you a formula which roughly said that this homotopy limit can be identified with the derived torsion, with the torsion of x, with gamma ax. And then by using some universal property of gamma a, we can, if we have gamma ax here, we can also put gamma ay there, and we're fine. So I mean, it's some game, but it seems it's behaves really, really nicely in that setting, more than I would expect. That really this abstract triangulated completion functor interacts on the compacts really well with the non-derived action, with the homotopy action. Okay, but then maybe we can dream even a little bit more, and I call this Cauchy completion of triangulated categories, but this is not really, in some sense, the terminology is unfortunate because the Cauchy completion of an enriched triangulated category is a concept which means something slightly different. So that's why I put it in quotation marks. But okay, so the idea here is that we have the big category of torsion dualizable objects. We have a smaller category of torsion compact objects which doesn't contain the unit, right? And really naively, the torsion dualizable objects somehow model the completed ring or should be related to the completed ring, whereas the torsion compact objects should see its torsion quotients. That's at least how it worked when T was dr for an ordinary ring, right? And we can very naively ask, because of course this completed ring is some inverse limit of its torsion quotient, whether we can in some such way reconstruct dualizable objects from torsion objects, right? And some weak evidence is that there are such reconstruction phenomena known. So Henning Krause and then Amnon Neeman, especially Amnon Neeman with his metric completion, he gave some method to reconstruct, or they produced some methods to reconstruct the bounded derived category from perfect complexes. And the relation between the bounded derived category and perfect complexes are in some way similar to the relation between compacts and the dualizables. But okay, I mean it's really a little bit cheating, right? So this was this relation between perfects and dualizables was for non-commutative rings, so there is no monoidal structure, or at least no obvious monoidal structure. Whereas here we rely on monoidal structure, and then then there is some home pairing between perfects and dualizables, and in here between compacts and between perfects and bounded derived category there is some home pairing, typically pairing with respect to home, and here we have some tensor pairing. What do I mean by that? So we have some lemma which works for this gamma at, but it's even much more general. I mean, it just needs some abstract assumptions. So if we take a compact object and a dualizable object, so quite generally compact tensor dualizable is compact. If you just write down the properties, you will see it quite quickly, right? If you look at the definitions. What is more interesting, that if you take an object D in this gamma at such that tensoring D between every compact is again compact, then the object actually has to be dualizable. So this is some kind of this is a kind of characteristic property of dualizables. You can characterize them like that quite generally. And you can characterize compacts in a dual way, but actually C is much easier, because if you have an object such that if you tensor it by any dualizable you get compact, then you can tensor it by the tensor unit, because the tensor unit is dualizable and you see immediately that it's compact. So B is actually slightly more intricate, but it's not too hard either if you have reasonable assumptions, and not that quite mild reasonable assumptions actually, right? And okay, and so now the result. It actually turns out that it works better than we would hope at the beginning. We can actually reconstruct the dualizables from the compacts as a triangulated category without any enhancement. So in that sense, it really looks similar to Anno Neemann's results. But the setting is actually has also quite important differences, which I want to mention. The reconstruction is quite relies on the monoidal structure, which makes it a little bit more technical, because this gamma AC is a tensor ideal by the previous lemma of dualizables, but it doesn't contain the tensor unit, but it contains some sequence of approximate units. Because gamma A1, it was here a few slides few slides back, right? So we had this system, this direct system. So it doesn't contain the tensor unit as such, but it contains some sequence which behaves as a sequence of approximate units. So it contains some information about the unit, and if you formalize it reasonably, then you can actually reconstruct gamma AT from gamma AC with all the structure, including some shadow of the monoidal structure. How would we do it? I mean, it's not surprising. At the superficial level, we can do the same as Amnon Neeman is doing, right? We can look at the functor category on the compacts, right? Which becomes a closed symmetric monoidal category with the deconvolution product. So the deconvolution product is something which more or less by definition makes the Yoneda embedding compatible with the tensor product, right? So we basically take the Yoneda embedding, we have some tensor product here, we extend it by colimits in both variables. The tensor unit is a bit more tricky because the tensor unit is not here, right? But what is the point? That basically using the previous theory and the game with Mittag-Leffler sequences and so on, we can prove also that the tensor, okay, so here we have the Yoneda embedding. Okay, so it extends, sorry, here I shouldn't have compacts. Here I shouldn't have compacts. Sorry for this typo here. So there is the honest Yoneda embedding can be extended to a restricted Yoneda embedding from all of gamma AT to the modules where we send X in gamma AT to the restricted home, right? We take home, but we restrict it only to TC. And this actually induces an equivalence on dualizables. So first of all, this functor extended to all of gamma AT, this restricted Yoneda functor is by no means fully faithful, but if you extend it only a little to dualizables, it still is fully faithful. This is something which we share with the setting of this pair perfect complexes versus DB. It is also possible to prove something like that. But now we can even identify the essential image because this mod gamma ATC is again closed symmetric monoidal with the deconvolution. And the dualizables here are also the dualizables here. So using the monoidal structure, we can reconstruct it as dualizable functors, right? And then as with Amnon Neeman's case, modulo some technicalities, triangles of dualizables are suitable colimits of triangles of compacts, right? So here you see that dualizables are, on this side, dualizables are colimits of compacts. Honest colimits, not just homotopy colimits. Right, and then because here there is nothing triangulated here on the right hand side, right? And so we can really play colimits, but then we can take triangles here, transfer them here by Yoneda and play with them sufficiently long to prove that triangles are just triangles. But this does not come for free because expected, because they didn't come for free also in Amnon Neeman's example. But we have to deal with some differences, right? So our setup, so in some aspects our setup is much worse than Amnon Neeman's setup because Amnon Neeman's proof relies on some metrics from T structures, right? Some properties of T structures. But what we assume is not friendly to T structures because it may very well happen that your ring has invertible elements, units of non-zero degree. But if I have a unit of degree n in the ring and the ring acts on your triangulated category, it so happens that the nth suspension will be the identity functor. So the suspension functor will be periodic. And there you hardly ever can have T structures which are kind of non-degenerate at least, right? Or bounded. Because then every aisle or coaisle will be a thick triangle, thick subcategory, and the heart will be trivial and so on. So T structures degenerate in that setting. So we have no T structures. Also, one feature which Amnon Neeman used from T structures is that if he took an object dB, he approximated it by some sequence of perfect complexes by basically taking a projective resolution and taking brutal truncations. And the thing is that if you take Hom to any other compact, right, if Y is any other compact object, then this sequence stabilizes. this inverse system of Hom group stabilizes, because at some point y doesn't see any difference between the terms, right? And this doesn't happen here either. The sequence in our case is also special, but in a different way, or in a weaker way. It's Mittag-Leffler, which means that it's essentially, if you don't know what Mittag-Leffler is, it's some stabilization of images in the inverse system, but it's very close to an inverse system of surjections. You can essentially think of it of an inverse system of surjective maps. So basically, morally, our systems do not stabilize, but we get systems of surjections. But on the other hand, we have some strong tool which Neeman didn't have, and that's the monoidal structure. Or at least he didn't have it in the most general versions of his result, right? And I should finish now. So, okay, so very quickly, if we throw in some more assumptions, then we can prove even better. So I will maybe go quickly through this side. So Uh, uh, we want some. So if we can assume that we are in our situation, and our category of compacts has a strong generator. So strong generator. So sorry again for a typo. This small g here should be the same small g here. So we may assume that we have a generator, compact generator of T, but in such a way that every other compact objects could be obtained using only a bounded number of extensions. Okay? So this is an extra assumption. It's quite strong. So for commutative Noetherian ring, this really forces the ring to be regular of finite Krull dimension. Right? This strong generator. So we can say something similar using some similar assumptions for commutative Noetherian rings. But for example, in the module representation theory of groups, this is always satisfied. Because here the compacts is the bounded derived category of the group ring. And the bounded derived category, the group ring has finite level length. It's a finite dimensional algebra. So we can, so there are finitely many isotypes of simples. And we can, the strong generators would be just injective envelopes of the simples. So here it's always satisfied. And if we trust some results, then also for the finite group scheme, it still is satisfied in interesting cases. Okay. So we just need to assume that the base ring is regular. Nice enough, I should have said also regular commutative Noetherian probably, and G should be, so far I can extract it from the literature only for commutative group schemes. Okay, so strong generation could be thought of some regularity assumption, and then what we can prove. So if we have a T and some acting ring and some A as always here, and if G is a strong generator for the compacts, then also the dualizables, the torsion dualizables and complete dualizables have a strong generator, namely the obvious one. So it generates that, right? So there is some result which looks similar, but it's incomparable as far as I can say, by Balmer and Sanders, where they look at derived categories of commutative Noetherian rings. So they look at derived category of commutative Noetherian, or also not only Noetherian but many more rings. They do not assume strong generator, but their category is much more special, and they prove something they prove something similar, but they also say that this is a generator and not a strong generator. But okay, if we are happy with strong generator, like in the module representation theory of groups, which can prove that, and if you view the existence of a strong generator as a regularity assumption, this actually makes sense, because it says something like that the completion of something regular of finite Krull dimension is again regular of finite Krull dimension. Okay, if you want some maybe intuition or heuristics or whatever I can call it from that. And then we can again, but in that case we can do even better, because we can again really recognize dualizable objects. In this case, complete dualizable objects by cohomology. If we take a complete objects and we put here any compact object, not necessarily complete compact object, any compact object, Then dualizability is equivalent to having finitely generated Hom R module, right? So again, from commutative rings, for commutative rings, the analogous condition would be that you can single out perfect complexes over the completed ring by looking at cohomology. So which of course needs regularity because this is something like comparing dperf and db. Okay, or equivalently, I mean, you need not need, of course, to test it on every compact, but you can take just the generator. This is good enough. And now I should finish, so I'll just show you the last slide very quickly. So what it says that basically in the existence of a strong generator, there is something which could be that Hom also the usual Hom just the ordinary Hom groups, but graded Hom or R modules give you a perfect pairing in the sense that Hom from a torsion compact to a torsion dualizable is a module which is not only finitely generated, but it's even torsion R module, a-torsion, and then then of course this Hom gives you two embeddings, one from dualizables to functors on compacts, right? And one from compacts to dualizables. And of course, Hom functors are cohomological or homological, but they are characterized by this property. And this is actually obtained by putting everything before together. And something very similar was again proved by Neeman for commutative Noetherian rings and for the relation between dperf and db. But he did not need any strong generator. He had different assumptions. Here it seems, needs a strong generator. So I don't know what the correct comparison is, what the intuition or heuristics is here. This is just what we could prove. Okay, that's all. And sorry we started a bit late, but not as late. So sorry for for going over time. Thank you.
Thank you, Jan. Let's all give Jan a round of applause. Okay, if you have any questions for the speaker, please ask them.
I have a question maybe. So
No
going back to one of your first slides, maybe where you had the derived category of a ring, and then you had this ideal. How important is it that you look at V of A? Could you look at some other subset of spec and do something similar? Or
I suppose you can, but I don't know what you can prove because, of course, then you lose some finiteness. But at least you always get a recall more. But the torsion radical can be described in a similar way. I do not know about a completion because then it would be some more complicated completion, right? The limit would be not only about powers, but real limits about some Gabriel filter corresponding. Actually, I do not know. I would need to check. I suppose. I mean, there are the obvious candidates, and the question is when everything works
yes,
and when it
yes.
fails, and that I don't know so well.
Okay. Thank you.
Thank you, Henrik. Zihan, you have a question?
Yes. Can you hear me?
Yes, yes.
Yes. So I have a general question. So like you have this monoidal structure. For example, we are thinking of dr where r is um, commutative. So how much of the theory works if we look at r non-commutative?
With this paper, I really do not know because we basically use the monoidal structure all the time. So, okay, strictly speaking, of course, for group algebras, we have a non-commutative ring, but it's a co-commutative Hopf algebra. So where was it here? So we need some commutative monoidal structure here. So I do not know, we haven't been looking at that, what we can do for non-commutative rings in general. The technology would need to be different, certainly. I know that Amnon Yekutieli with co-authors, he has some theory for derived torsion and completion and weak pro-regularity, which is the relevant weaker condition than being Noetherian in the commutative case, so that the derived torsion and completion interact well. But I really do not know enough about it to be able to tell anything useful now.
Thank you.
Thank you. Any other questions? So in Amnon's setup, he is doing it for like an approximable triangulated category, and then there are some extra assumptions, and he's basically having a connection between TC and TBC. And here you have a different setup, obviously, and they don't, I mean, none of them are specializations of the other. Could you imagine like a even wider context such that both Amnon's situation and your situation could be dealt with together? And also, I should say there is a newer paper by Giovanni Rosanigo, who used to be a student of Szczeciński, where he does Amnon's things in the enriched infinity category setup, and he gets like more results. But of course, you have to assume the stable infinity model. Anyway, so can there be a more general setup?
Yeah, that's a good question. I don't know if I'm able to say anything too clever. So here on this slide, we have some features which we identified. So for example, we have some inverse systems which they do not need to stabilize as they do in Amnon's case, because he uses, what did he call these sequences of elements? He called them these eventually constant. Here, these classes L and C.
Strong approximating systems.
Yeah, he had some
Cauchy
completion.
sequences. Cauchy
Yeah,
sequences with respect to, yeah.
one was Cauchy sequence, but the other was compactly supported Cauchy sequences, right?
Oh yeah.
For example, this is one possible weakening of compactly supported, but I really do not know what is enough and what is not. So I mean, if you have any ideas, guesses, results, then I mean, of course, I will be interested. And thank you for mentioning this other work by the former student of Szczeciński.
Yeah,
I don't know about it. So
it's
I
not
would.
on the archive, but it's on his website.
Okay. Thank you.
Yeah.
I will look at that, but I cannot comment on that now. So maybe, but I don't know. Here are some candidates, but maybe more conditions will be needed.
Sorry,
I just
sorry, well, Jay?
I just have a comment on this. If you look at the standard approximation of the unit, for instance, or the standard approximation with causal objects, all the maps have the same cone. And basically, the length of a morphism in Neeman setting is a size of the cone. So you will get maps with uniform length. So it cannot really work
Yeah.
the same way.
Yeah, the setups are very different, and also the methods are completely um, different because you can't use these structures, as you say. One other question I wanted to ask Jan, which was that so there was this work by BIKP where they showed that the thick tensor ideals of like gamma p star mod kg, the dualizables of gamma p star mod kg were in one bijection with specialization closed subsets of what was it spec H star GK be completed. So those kinds of results, can those kinds of results be just special applications of what you are doing here?
No,
Like,
the stratification is a problem. We barely failed there. We didn't find anything better abstractly. I mean, there we really hit the problem that we are working only at the level of homotopy categories in some sense. It seems in general quite hard to relate. So what we can do, right? So we have some. Uh, if you want some stratification, then you need to relate some Hom modules to some generation in the triangulated category, and this doesn't seem interacts so well. So even if we know that T is stratified, then we do not know whether gamma AT is stratified, except for the cases maybe proved by BIKP, where it works. They proved it works in their setup. So I really do not know.
I see. Okay. Thank you again. Any other questions? And thank you, Jin, for that comment. Any other questions? If not, let's thank Jan once again. We have Paolo Tomasini from, not from Trieste anymore, from Luxembourg next week. Yeah, see you then. Jan, can you send me these slides afterwards?
Yes. I maybe will correct some